Welcome, Ben, also known as Ben Rein or Dr. Ben Rein, or on Instagram as Dr. Brain. Welcome.
Thanks so much for having me. I appreciate you bringing me on.
I am so excited to talk to you because I love neuroscience, and I just want to first find out how you got into neuroscience. Is this something you've always been interested? What led you down that path?
Yeah, awesome question. I started off in psychology. When everyone goes through that process, you get to college and it's like, what do I want to do with myself? And mine was, I think I'm interested in understanding why people behave the way that they do. And so I started off studying psychology. And then my second year, I had this unbelievable nightmare that completely changed my life. And the nightmare itself has some deeper meaning and stuff. And it's a kind of a long story. So I'll spare everyone. But bottom line, I woke up from the nightmare thinking, wow, that was unbelievable. I can't believe my brain could create such vivid imagery, and I can be so completely immersed in this experience, but also not being aware that my brain is generating the experience. And it made me realize that, yes, I was interested in why people behave the way behave the way that they do, but I was more interested in like, what are the mechanisms of how the brain regulates all those behaviors. And just the complexity of that dream kind of opened my eyes to the complexity of the brain. And I had been very nervous about taking those upper level classes, those molecular biology, biochemistry things. I wasn't sure if I could do it. And this dream was like, okay, I feel like if I don't do it, I'm going to be regretting it the rest of my life. And so I made the transition, and I'm extremely glad I did. And I was fine in those upper level courses, it turns out. So, and I don't think that's any credit to me. I think it's just if you want something really bad, anything becomes easy as an obstacle. So I strongly encourage everyone out there to just pursue those things, even if there's barriers that you're afraid of.
I like that because some of those things, as we know, like from PT school and all that, is we have to take them, and there's probably the the application isn't exactly used in daily life. But what I even tell my kids is like the effort and the work that we do in those classes is in some way preparing us for how we'll apply other knowledge. So I agree with you. Don't be scared of them because maybe you'll never use them in real life, but there's something you're going to get out of it.
Yeah, absolutely.
How would you define neuroscience? I mean, I think it's pretty obvious, but not everybody would know necessarily.
Yeah, I would define neuroscience as the study of the brain and its function, and maybe include in there its disorder.
Mm. So, can you briefly, for like a Brain 101 session here, a little bit, can you talk about the brain? I think people can picture it, they've seen it anatomically, but it is so complex. It's just a genius computer beyond what we could ever really simulate or create. Can you talk about the different parts of the brain and what they're responsible for? And perhaps like in our everyday life, what are where does those different parts of the brain show up?
Yeah, I love this question, and I never get asked this, and so I'm excited. And I could talk for like two
Woo!
hours right now, but I won't.
I know it's a
Um,
really hard question. It's like there's a lot of parts of the brain, Laura, but yeah.
well, yeah. So I want to start even more fundamentally at just the brain itself and how it operates. Um, you have billions. I think it's 80 billion neurons, brain cells, and they interact at these junctions called synapses. And so this communication between brain cells is absolutely critical. It underlies essentially everything. It underlies your emotions, your cognition, your sleep, all of these things. And so what we find is that most drugs that, even things like anesthetics or painkillers, a lot of these things, they all kind of come down to affecting the way that these synapses transmit information. And that in turn affects the activity of the brain. So what we have is billions of neurons communicating, but they're all divided into sort of discrete brain areas. And the brain areas tend to communicate with one another in sort of specified relationships. So like everyone's brain, we all have the same relationships in our brain between the different brain areas. And so each brain area has many, many functions, but it also has those functions are sort of specified by the interactions it has. So one brain area might be involved in I'm making this up, but let's say it's involved in empathy, and you feel bad for someone else, but maybe in a context of, ooh, I feel really like bad for the way that person's hurting right now. But that might be regulated by a relationship between that brain area and a different brain area. But in the context of like, well, I'm really scared for that person right now, and I think that there might be in harm's way, that might be regulated by a connection between that same brain area and a different brain area. So this is sort of complex, which I didn't use that example, but there's just a whole lot of interaction between all these areas, and those circuits are really what neuroscience is starting to move into in terms of looking at like what are each of these circuits doing rather than the brain areas individually. So as far as brain areas, there are many, many, many ways I could go with this. There are many brain areas. I'll choose a few. So some of the most common ones that people talk about, the amygdala is a brain area that's been very much highlighted in the public realm, I would say, and it's involved in anxiety and emotion and fear. The frontal cortex, prefrontal cortex, is involved in like higher level cognition and advanced thinking, higher level thinking, type of brain area that develops much later in life relative to other brain areas. So maybe around age, I think they say 25 is like
So
when
this
it's
is,
fully
for
developed.
instance, the area when they say 18-year-old teenage boys are making not great decisions because their frontal cortex is not fully developed and they can't kind of see like the danger or the choices they're making, that kind of thing, right?
Right. Yeah. I tend to describe the frontal cortex as the babysitter of the brain. It's sort of like the mature area that's like telling the other brain areas to relax and maybe not do those things. Maybe not say that thing right now. You might insult that person. Maybe don't jump off that cliff into that rocky water. You might get hurt. That is your frontal cortex. And actually, it has a very strong relationship with the amygdala. And so, as you gain emotional maturity throughout life and you get better at things like suppressing a harmful, mean comment because you're angry, that is your amygdala saying, wow, I'm so angry right now. I really want to do this horrible thing and hurt this person. And your prefrontal cortex is saying, don't do that. So that's why I like to call it the babysitter. It's the sort of an emotional maturity center.
Hold on one second, Ben. I'm going to let my dog out.
Sure.
Okay, we're back. So yeah, how about the left and right hemisphere? We also hear a lot about that, and like, how do these two different hemispheres communicate with each other? What are the different jobs of the left versus the right hemisphere? And then we'll go into the next question, which is a lot of people really identify as being more dominant on one hemisphere or the other.
Yeah. So the left and the right hemisphere are largely identical. Almost every brain area is bilateral, meaning we have one on each side. And in almost all cases, they do the exact same thing on either side of the brain. There are a few exceptions. For example, in the left hemisphere of the brain is where most of our language processing and speech production happens. And on the right side of the brain, that area is used for sort of other things. But the main difference between the left side of the brain and the right side of the brain is sensory. So your right side of your brain generally receives sensory input from your left side of your brain. So it's reversed, and your left side of your brain receives the input from the right side of your brain. Same thing is true for like your vision. Your left side of the brain receives input from the right visual field, and vice versa. So getting to your question about whether people have a dominant hemisphere, that is one of those brain myths that has sort of been debunked. I'm not sure where that one originates actually, but yeah, the whole like left brain, right brain thing, it's there's no evidence for that. There's been at least one study that I know pretty well that they just looked at resting functional brain imaging in like 1,000 people. And they just saw that when people are hanging out, there's no preferred brain side. There's no increased activity in either side. What they did see is increased activity in certain areas that we know are lateralized, like the language centers. So for example, the left side of the brain might be more active when talking than the right side of the brain, specifically in the region that controls that function. And the way that the two sides communicate is through a very large structure called the corpus callosum, which is basically just a huge bundle of wires that connects the two.
That's so fascinating. So if somebody was left-handed versus right-handed, is that a random thing? Is that based on one side, maybe developing earlier? What would be the root of that? Or are they still not sure?
I I don't know. I'm not sure if science knows. It's a question I'm really interested in myself because I would be inclined to believe that it's somehow genetically, like there's some genetic predictive
Definitely.
factor, right? But I'm actually not sure if like left-handed parents are more likely to have left-handed children. And also it's hard to separate, is that because the child watches their parent writing with the left hand and they just automatically pick it up? Um, Tough thing to study, but I would
It's
bet there must be
fascinating
some
because in
answer.
history, many, many brilliant people have been left-handed. My mom is left-handed, so she always points this out. And so it kind of poses the question, are left-handed people naturally, is there something about the way that they um, code that information or download that information that is more permanent or easier for them because of that dominance? Who knows?
Yeah, I mean, and I would hypothesize that once you establish a dominant hand, left or right, the brain area that controls your hand, your motor coordination, it's very fine motor function, that the brain area or areas that control that become interactive with the same brain areas, regardless of whether it's your left or right hand, and whatever, regardless if it's your left or right brain. I'm sure they just establish a relationship with the language parts and whatever other brain areas integrate into writing. But it's such a good question of like what makes that happen in the very first place, and it's really interesting.
Yeah, I agree. There is obviously, I think, some genetic, and that could be modeling, or it could be, just like kind of like the genetic coding for that. I'm curious. Can you talk a little bit about the motor cortex and what happens, for instance, if someone were to get bedridden and in that area? Is there any research or anything that you know about that impacts the motor cortex when you're not moving?
Yeah, so the whole brain is very much use it or lose it. A lot of neuroscientists like to say. Um, I constantly refer to the brain as a muscle. I mean, of course, it's not actually a muscle, but it behaves like a muscle. If you go to the gym and you exercise your biceps all the time, your biceps are going to get really strong. If you sit down every morning and you do a Sudoku puzzle, the parts of your brain that are activated when doing that puzzle get stronger and stronger, and you become better at solving those puzzles. And the brain has to be this way because we must be able to learn. We must be flexible in our brain function. And then the same is true, the same physiological properties of the brain that are controlling things like solving a Sudoku puzzle. The same cellular activity is the same thing that underlies something like motor coordination and movement. So when you're not moving, when you're laying in bed for an extended period of time, it's not so much that your brain cells are going to die or anything like that. And especially with something as important as motor coordination, I would bet that it would be very delayed. Like you'd have to be bedridden for a very long time before you actually lose any function because it's so important. Versus on the other hand, if you stop doing Sudoku puzzles for a few weeks, you might pick up a Sudoku puzzle and say, "Well, I'm really not as good at this as I used to be," because it's not an essential function. Whereas moving is so important for life. Um, so I think what would probably happen is first, if it was an extended bedridden period, your muscles would atrophy a little bit. You would become your muscles would weaken, and your brain would get it. I'm sure it would lose the activity, or it would be so devoid of activity for such a long period that it would just become a little bit lazy, maybe, and kind of careless, you might say, and less precise. The activity wouldn't be as precise as you might see in someone who does like gymnastics or yoga. But that would be you'd be able to regain that, and I do think there'd be some interaction. The muscles are weak, the brain is weak. When you first get up for the first time, you start walking around, you're just some incoordination, you're having trouble with balance, things like that. But I would bet it could all be regained. But I do think
Mm.
age is a factor there. The older you are, the less plastic your brain is. So if this is happening to someone when they're 85 versus 20, the 20-year-old will respond much better and regain that function much more quickly.
That's a great point. And you mentioned delayed firing, which I think is so fascinating. That if we don't use something, whether it's our language capacity or solving a puzzle or moving in specific ways, it's not that you lose that. It's just that it's slower on the uptake. Is there anything that you think, if you were to recommend to someone, like how to best improve their motor firing so that they're having a better response in terms of motor, motor response or brain response? Like if you had all the time in the world as a neuroscientist, you're like, these are the things I would recommend people do every day to keep that firing really crisp.
Yeah, I mean, so like I said, the brain's like a muscle. And I also mentioned in the very beginning that the brain functions through these signals being passed between brain cells and brain areas. And what really happens when the brain is changing like a muscle, what's happening is certain brain cell connections are growing stronger. And one brain cell talking to another brain cell, it suddenly becomes much more powerful. So there might be more neurotransmitter being released, or maybe there's more receptors on the receiving cell. And so these signals, one cell might send a little action potential and release its neurotransmitter. And when I say neurotransmitter, I mean something like dopamine or serotonin. You've heard of these things. And when it releases that signal, the response is bigger. And so this happens. This is called plasticity. It's synaptic plasticity. And it's really hard to like increase plasticity by doing anything like taking a drug or something like that. And I wouldn't recommend that anyhow. But just repeated action, repeated activity in these brain cells and in these connections is what's really going to drive their changes. So if there's a specific movement that you want to get better at, like you want to practice juggling, for example, just do it as much as you possibly can. Really, it's kind of a lame, like hack. It's not a hack at all. It's just like practice makes perfect. But that is really just how the brain works. And so,
right, because those signals become stronger and crisper, and like you said, then that leads to better coordination, response time, and all of those different things. And I also think it's really fascinating. Maybe you can tap on this for a moment. That parts of the brain, when you think about a movement, when you think about like what is involved in it, those parts of the brain light up without you even doing it. How important is this concept of visualization? Obviously, you need to then manifest it, but can you speak about like that's so fascinating to me, like the visualization part of it?
Yeah, like visualizing a movement versus actually doing it.
Yeah.
I don't know too much about that. I mean, my belief is that, imagining something probably activates, well, like you said, if they're depending on the context, probably activates the same brain areas that would be activated if you were actually doing it or actually experiencing it, whatever it is. But it's probably to a much lesser level. This maybe to the point where it wouldn't make a difference. Again, it all depends on the context. So let's say someone's bedridden for weeks and they're imagining themselves walking. I would bet that maybe it has a small effect, maybe small, maybe not even detectable through a scientific study, but maybe some effect. But it's better to do the behavior because after all, the world is unpredictable. And imagining walking, you might not imagine yourself stumbling and falling and regaining your balance. But when you actually do walk, you might experience something different and unexpected. And that's really where the brain learns, is from failure and correcting based on unexpected activities.
Yeah, so let's talk about yoga. How do you, and I know this isn't where you're studying and we're going to get into your research, but how do you think yoga benefits the brain?
That's a real good question. I mean, I think yoga is amazing. Let me just start by saying this. People always ask for like brain hacks and, like what supplements can I take to do this or that? And I really think that the very first intervention that should be made, especially in the context of mental health, if you're feeling a little bit down, is just some sort of behavioral intervention, something like mindfulness meditation, yoga. And there are plenty of studies showing that yoga can actually reduce symptoms of things like depression and anxiety. I think even like PTSD. It can have a mild effect, at least the study I'm thinking of, in reducing blood pressure. And so how it's actually working on the brain, not scientifically validated or backed. This is just my opinion. I think that when you're experiencing stress, something, any sort of unpleasant feeling, and you can remove yourself from that, and you can actually like stop processing the stress and stop your physiological stress response, that's just as good as solving the problem completely. If you can just stop feeling the stress truly, like all the way through, then I believe that you're fully removed from the stress. And so the physiological harm of the stress is gone. And so I think something like yoga, where you're breathing, you're relaxing, you're focusing on something that is not only not stressful, but actually extremely peaceful. You're focusing on your breath, you're focusing on your movement, you're focusing on improving yourself. I think it's just sort of like, it's like the equivalent of like dipping your brain into a nice warm spa. It's like your brain
I
is just
love
getting
that.
this little vacation from your everyday stress. And I really, really think that people having um, this skill of introspection and being able to look inside and realize I'm stressed. I need to remove myself from this right now. Even just a 10-minute yoga session right now, anything, some breath work. That skill is so important, because if you can relieve the pressure and the physical feeling of stress, you're able to, whatever the process is that's occurring in the brain that's driving the negative stress response, if you can remove yourself from that, then you're going to preserve your brain from any more damage from that stress response.
Now, I know there's a lot of parts of stress and stress relief, but can you briefly describe like what are the mechanisms that are happening when we practice mindfulness and decrease stress? Like what's happening in the brain beyond just not our thoughts, not thinking about whatever it is that's creating the anxiety, but what is physiologically happening to lower our stress response?
So I mentioned at the beginning the frontal cortex and how it's the babysitter of the brain, I like to call it. There are studies showing that stress, especially chronic, like long-term stress, just really bad for the frontal cortex. It can really impair its function. And so, you might have noticed if you're stressed for a long period of time, suddenly you become maybe a bit more impulsive. Maybe you become a bit less good at suppressing emotions. And if we care about
Writing
the
really, really not nice text and sending them before thinking about it.
right, suddenly you're getting in fights on Twitter with people. Um, but on a molecular level, what we've found is that in the frontal cortex with extended stress, there's actually a loss of certain receptors that allow cells to activate each other. And so overall, what this does is it lowers the activity of the frontal cortex, theoretically, because there's less positive, activating signals being passed around, or being received, I should say. And as a result, this lowers the ability of the frontal cortex to do its sort of babysitting duties on other brain areas. And not only that, but the frontal cortex is also really involved in higher level cognition and social behavior. And so, I find this personally, if I'm stressed or if I don't get enough sleep, I'm in a social situation, I'm just like, what did I just say? That was, yeah, I am not myself right now. And I am acting so awkward. I don't know what to do. I think that that's related to the stress effect on prefrontal cortex. And there's evidence to support that.
I would agree. I mean, I worked with traumatic brain injuries, and often there was an injury to the frontal cortex, and it was kind of not funny, more sad, but that inhibition that you're talking about is lost or really decreased, and that's when people say whatever's like there's no the filter has been impacted,
Mhm.
but also so not only are you not going to be socially very adept, but like you said, just kind of that high functioning of daily life is going to be impacted.
Yeah.
Speaking of like organization in the brain, can you talk a little bit about this very common diagnosis of attention deficit disorder? I don't know if that's something I know you have done work with um, atypical kind of neurodisorders such as autism, and so ADD isn't really that. But what is ADD? Like, how do people know they have it? What is the best thing to do? How is medication help or not help?
Yeah. ADD has become really well, I don't want to say popular, because
Yeah,
that sounds like people have,
yeah.
been getting it. What I mean is it's become very much sort of the focus of public discussion. I see
Hmm.
a lot of videos on TikTok. It has become a very popular discussion topic, I should say. And as a result, I think a lot of people are suddenly realizing, oh, I might have ADD. But I do think that there are a lot of accounts on TikTok. In fact, I don't think I know that there are many accounts on TikTok that will say something like, oh, do you ever, do this or that? Well, you probably have ADHD and follow me. And I have a book that you can buy. And, it always seems like that. But, in my opinion, I'm a scientist. I think that if you suspect that you might have ADHD, so if you're having trouble with attention or focus, which is a very common thing that people experience all the time, especially in the context of stress or sleep deprivation, then you could look at it and see if you can see a specialist and potentially get an ADHD or ADD diagnosis. The mechanism underlying ADHD is complicated and we don't really know. There is evidence that dopamine is involved. So, people often think of dopamine as sort of a pleasure or motivation molecule.
Like the feel good thing, but it's more than that. Yeah.
Yeah. So, but dopamine is also really important in like if you're trying to figure something out and you're motivated to pursue the answer, you're learning something, you're focused on it. You're really curious about what's the mechanism of ADHD. And so you do a Google search and you get a few searches in, you go through a couple of pages and all of a sudden you're like, oh, I just, I'm not motivated to do this anymore. I've given up. I'm tired. Or I'm interested in something else right now. Forget about this. Having that sustained dopamine in, I'm very much like, this is not neuroscientific.
Generalizing. Yeah.
Generalizing. Yeah. But dopamine may be an important signal for continuing that motivated focus. And so there's evidence that things like genetic mutations affecting dopamine are at play in ADHD, and the medications that are used are often targeting dopamine and enhancing dopamine. So how exactly it's working molecularly, I'm throwing my hands in the air, shrugging, but it's definitely, any of these conditions, ADHD, autism, depression, anything that really sort of affects like outward brain function or mood. These are all just like super complicated, multi-factor conditions where there's so many things happening and we're sort of like layer by layer peeling it back and trying to figure out like one thing at a time. But it's complicated because it's not that everybody who is diagnosed with ADHD has all of these layers happening. It's that like a subset might have one biological change, another subset might have a different biological change. And so we're figuring things out little by little, but it doesn't necessarily mean that any sort of treatment that targets that biological change will be impactful for everyone.
Right. Well, is there something like that? We live in kind of a attention deficit demanding world. We're just bombarded with so much information. Is there something that like you think is really a practical way to without even having a diagnosis of it, but feeling scattered? Is there something that you do or you recommend just to help people feel like a little less scattered and more, and help hone focus?
So I don't really have much to offer on this. I have narcolepsy, which is a sleep disorder where you fall asleep really quickly. And so I'm really tired all the time. And so personally, I'm prescribed Ritalin actually, but it's mostly given to me just to keep me awake. It keeps me alert.
Has that been something you've had for a long time?
Yeah, I was diagnosed when I was 13 years old. So I was falling asleep in my classes, and I got a sleep study. And the when you fall asleep and you go into the REM stage of sleep, which is when you dream, you kind of slowly descend through these multiple phases and then come back up. And that process to get into REM takes about 90 minutes. For me, it took 6 minutes. So I close my eyes and I'm
You're
dreaming.
A fun date.
Yeah, so I'm out. And so, there's always this sleep pressure throughout the day to fall asleep, right? Because it's when dreamland is 6 minutes away, it's awfully compelling. And my body's saying, well, I'm kind of tired of this task right now. How about a nap? So anyway, I'm prescribed Ritalin, which is what's prescribed for ADHD. And, of course it's hard to differentiate. Is this making me feel more alert or is this making me feel more focused? Am I more focused because I'm more alert, but,
well, I would say yes. It's probably like coffee. I don't think that that's just, something like, I don't think that's a placebo. When we drink a little coffee, we feel more, for those of us who are coffee drinkers, you just feel like more awake, ready for the day. And so
Mhm.
there's got to be, it's the caffeine, it's the, what you're having is some kind of, like an adrenaline that you need to wake up the brain so it doesn't think it's time to go to bed.
Yeah, and I mean, I guess this kind of gets at like same thing with like the left right handedness. It's like, is it because it's a genetic thing or is it because it's a learned thing? And this, it's like, is it the energy or is it the focus or is it both? And this is sort of a common problem that scientists have to face of like separating out these variables to really get at the root answer of something. And that's where really clever experimental design comes into play, and we can try to control for as many factors as possible. But sorry, this was a real big aside from your
No, I think that was
question.
great, and it reminds me of what my brother, who is a psychiatrist, will say to that point is there's many things we don't exactly know, like which causes which, but if something improves the overall, feeling or ability to focus, ability to, feel better in life, then we go with that, even if we don't know exactly the mechanisms of, which part is affecting the other. So I think
Yeah.
that's what's interesting about science is that just like our brain, it shouldn't be hardened. It shouldn't be like, this is the answer, this is what we have to go with. So now, speaking of science and research, talk a little bit about your specialty. I know I've asked you a lot about the brain, and and it is such a complex organ, but you have specialized in certain aspects of neuroscience, and I'd love to hear about it.
Yeah, I did my PhD research in autism, studying how genetic risk factors that are associated with autism change brain function and alter those interactions between cells at synapses. So I spent a lot of time studying that. I looked at a few different genetic risk factors. And again, this is kind of one of those things where I was talking about the multiple layers and something like ADHD. In this case, autism is a condition that's associated with at least 100 high risk genes. And so,
Mm.
I spent an entire PhD studying one of those genetic risk factors, one of them. And
Wow.
I learned some, I hope that I contributed some important uh, discoveries to the field that we now are a bit closer to understanding why this genetic change alters social behavior. But one down, 99 to go. So
My gosh,
um,
that is crazy.
yeah, so there's just so much research to be done. And so after my PhD, I sort of stepped back and realized, I could spend my entire career studying all these genetic risk factors and probably make a dent. But first off, there are many, many other great scientists out there studying these things, luckily, because again, there are so many genetic risk factors to study. So there are many scientists already on the task. And second, I'm sort of more interested in social behavior in general, not necessarily why a genetic change leads to changes in social behavior, which I am interested in. It's a good way to study that. It's a good probe for social behavior. But I'm just more interested in like when I'm in a social interaction, when anyone's in an interaction, what the heck's going on? Social behavior is such a complex phenomenon. There's so many things involved. You're reading body language, facial expressions, you're conveying both of those things. There's tone, there's so much information processing. While all the main thing that's happening is you're trying to figure out what the heck to say. And you're
Mm.
trying to convey information in a concise way. And some people are better at it. There's some people have trouble reading facial expressions, things like that. And I'm just really interested in the brain processes that underlie social behavior. And so the project that I'm currently working on is studying empathy, but it's actually in mice. So all my research is in mice because they're actually very social creatures, and their brains, although very different from humans, have a lot of the same functions and brain areas, and so we can actually really learn a lot from them. So I'm hoping to understand actually mechanisms through which we can enhance empathy. Whether or
Mm.
not that ends up being translated and used in human beings, who knows? But if we can understand how we might enhance empathy in a mouse, um, we at least grow a bit closer to understanding how empathy works in the brain.
So before I go into that, I just think it's fascinating because you originally went to school for psychology. So this is really kind of layering into that and building off of that original desire, because you're now looking at the mechanisms of the psychological behavior that exists.
Mhm.
Can you define empathy for us? Because I think we all have an idea, but sometimes people mix it up with sympathy, and when they say I empathize for you, but empathizing is different than I sympathize. Can you
Mhm.
can you just tell us maybe not only the definition, but how it's played out differently in the brain?
Yeah. So a common definition of empathy that's used in research is sort of adopting someone else's physical, emotional state. And so a good example of this, and I can talk all about this, it's remarkable, is if one person is in pain or experiences something painful and you're observing it, the same brain areas that are activated during a painful experience are actually activated in the observer, in the bystander. And so this is a really good example of empathy because, like I said, it's some sort of modeling of another person's state. In that case, the brain activity is actually identical. And sure, you might not feel pain. You might not feel, ooh, ouch, but you might feel discomfort. If I hate to bring it up. This is like one of my least favorite things in the world. But if there's ever like a video of like a sports injury that's kind of uncomfortable to look at, it's like almost painful, and
We
especially
all
it's
recoil like, but it's, yeah.
yeah, and it's like, why is that so uncomfortable? Well, probably because to some level your brain is mimicking the activity of the brain in that injury. And there are many wild studies on this phenomenon, specifically this empathy for pain. Do you mind if I get into this? Because it's
Of
it's pretty
course.
cool.
I do want to ask one thing. Is it based at all, or is it based stronger if you yourself have experienced it? So say somebody has blown out their ACL, and then they witness somebody else, and they can truly empathize. Like, I've been there. But is the brain different for a person who hadn't had an ACL injury but witnesses it and also has that same recoil?
Yeah, I mean, anecdotally, it seems like the answer is absolutely yes, right?
Hmm.
Um, it's so I have a very close colleague who studies pain and empathy as well, and she brought up a great example of a mother. So if you're you're not a mother and you hear a baby crying, it's like, ooh, that baby's crying, maybe not so uncomfortable. But she recently had a child, and she described how now if she hears a baby crying, it's like it just activates her brain. She's just like lights up and is like, oh man, like, okay, that's, what do I do? I need to act. Um, and I think that's a really good example of how experience can really shape your response to something. And
Hmm.
I don't think there's actually any clear evidence on this, but I would suspect absolutely that if you've experienced a type of pain before and you witness it on someone else, that the empathy for that pain is more severe. And there is evidence that the closer your relationship is with the person, so if it's a spouse or something like that, you feel more empathy for them in that
Let's hope so.
situation. Right, right.
So in other words, what you're saying is empathy is not dependent on whether you've had the same experience. It's whether you are able to experience some level of the pain or emotion that person is experiencing. Is that correct?
Yeah, as long as you're able to recognize it as pain, right?
Hmm.
So, I think it's pretty clear if someone is hit by a car or something. Okay, yep, that's the painful experience.
Right.
But the same also goes for social pain. So exclusion, something like that. If
Hmm.
people are left out in the social setting or graded as really poorly right in front of them, things like that. That's painful. It's social pain for the person experiencing it. And there's also evidence that the same sort of thing happens, that a bystander, if they feel empathy for that person, if they recognize that the person is being emotionally hurt, then they also show the same kind of brain activity for that.
Okay, so you were going to continue, and I interrupted you with my example there of whether if it was something that we had experienced ourselves or not. So you're going to go a little bit more into your research.
Yeah, so this isn't necessarily my research. This is there are a bunch of studies that are just mind blowing, and I have a series of TikTok videos. So if it hasn't, I don't think we've brought this up. Aside from my role as a scientist, I also make videos on the internet, and describe cool
Yes,
papers
and
and
we'll
stuff
have
like
all
that.
those in the show notes because they're awesome. That's actually, that's how I found you. Because I
Yeah.
follow you. Yeah.
Awesome. Well, thank you. Yeah, I do my best. I think science needs to be much more accessible to the public. But this set of papers is one of my favorite that I've come across. So, like I said, the brain activates very similarly if you're watching someone in pain versus if you're experiencing, as the person experiencing the pain itself. Um, there are papers showing that first, if you give the bystander Tylenol, it reduces the level of pain that they report. So the level of discomfort. So they actually they rate the painful experience in the other person as less painful, and they rate it less uncomfortable to observe. So, and this is just sort of more evidence that watching someone else's pain activates the same brain areas as experiencing the pain itself. Because if a painkiller can reduce your empathy for someone's pain, it's probably because it's acting on those pain brain areas. Now we'll go
That
one
is
step further.
fascinating. Wow.
Yeah, so this just keeps tumbling, and it just becomes mind blowing for me, at least. So the next thing, if you give someone a fake painkiller, so let's say you put a topical, a cream on their hand, and you say this is a painkiller, and it's not. It's actually just a placebo cream, and then you shock their hand, they will rate that pain as less severe. So they will actually think that the painkiller worked, but there's really no painkiller. So there's something happening. They're perceiving I am in less pain right now because I think I'm in less pain, but really there's no like biological change. On the same note, if you give them the same situation, but you zap someone else's hand in front of them, they also rate it as less painful. So a placebo painkiller can also reduce empathy for someone else's pain, just like a real painkiller.
Oh,
Also
wow.
mind blowing. And now the cherry on top, my favorite part of all, if you give that person, after giving them the fake painkiller, if you give them a real drug that actually blocks opioid receptors, so drugs like morphine, these are really strong painkillers. They act on opioid receptors in the brain. If you block those sort of painkiller receptors, it blocks the effect of the fake painkiller. So it actually prevents the placebo painkiller from causing pain relief, which suggests that when you're experiencing placebo pain relief, it's actually activating these like naturally existing pain relief systems in the brain.
Wow. Wow. This is
It's
cool. This is amazing.
Yeah, I agree. I'm
The
glad you think
brain
so.
is so crazy. This is wow. So how could we how is this going to apply for us?
Yeah. Whenever I talk about this, I think people start to think, well, I hope that doesn't mean that my doctor's going to start prescribing me placebo painkillers. I definitely hope not. That I don't think that would ever actually happen. Of course,
Right.
Do no harm, right? If someone is actually in need of painkiller, they will get a painkiller. But what's interesting is that in like clinical trials of SSRIs, things like that, in a lot of the studies, the placebo has some effect. So you always need to control for the effect of giving someone a pill and saying this is going to make you feel better. So they always note that the SSRI or whatever the medication outperformed placebo because the placebo can actually make people feel less depressed. So I don't think that this should ever be harnessed for treating any conditions. The only application I could ever think of this is maybe like you call your psychiatrist and you really need an appointment, but the psychiatrist is booked for the next month. And so the psychiatrist says, okay, I'll see you next month. But until then, I'm going to prescribe you something to help you out. And it's actually just a sugar pill or something like that,
Yes.
And maybe it's like a holdover. I think if that's a serious situation where, especially if there's something like suicidality involved, obviously I would hope that the doctor would see the patient. But that's really the only context that I can imagine it being used is like sort of a holdover, like maybe there's some sort of effect. But I think it's so interesting that a placebo, in the case of a placebo painkiller, activates the systems that you would that the person is expecting it to act on. Because I would think, based on what we know about the brain, a lot of the time you see like compensation biologically. And so I would think that if you're expecting a painkiller, the brain would naturally go like the opposite way, or at least stay where it is. It's interesting to me that it goes the same way as the painkiller and activates the naturally occurring systems to potentially maybe enhance the effect. But the mechanism through which that happens is perplexing.
It is.
I
And
really
I'm
don't
sure
know.
just in general, like every day you're studying in neuroscience, it must be just like there's so much more I don't know because it's
Yes.
like we can't ever keep up with the complexity of the brain. And I'm sure it, you know, based on research before, that research changes too because new ways of studying are more specific or more elaborate and reveal information that wasn't available even a decade ago. So it's
Mhm.
like constantly changing and keeping up with it. So it's going to be a fascinating life, I imagine, that you're going to lead. And but I love that you're taking this incredibly complex organ and system of neuroscience, field of neuroscience, and making it so available for people on social media. How did you kind of make that leap and decide to get into social media and teach people what you were learning?
Yeah, it was sort of happenstance. It's funny, I'm realizing, I got into neuroscience because of a dream. It wasn't really a conscious decision. And I also got into science communication because of a randomly occurring event. Um, it was the very beginning of the pandemic in like April 2020. And I left my house for the first time since the whole thing started. And I went to Walmart, and I was used to wearing those surgical masks that now, everyone knows now. At that time, most people had never worn one of those. It was something that people wear in hospitals and research settings, maybe. So I went to the store, and nobody was wearing it right. It was like inside out or upside down, or people didn't seem to realize that you could expand it or clasp it to the nose. And I thought, people are going to be wearing these things. That should at least someone should show them how to wear it. And so I made a video I was intending to post it on my personal Instagram and Facebook just for like friends and family. Here's an instructional video on how to wear one of these. But I decided to film it on TikTok just because it was the only app I had where I could film a continuous 60-second video. Like Snapchat, Instagram, they like cut off at 15 seconds, and I didn't want that. So I filmed it on TikTok, even though I had no username or no picture or anything like that. And it got like 1.8 million views. It just, it just,
Wow. You're
it
like,
just blew
I'm
up.
onto something here. Yes.
Yeah.
Well,
And
it's
it's funny though.
useful and it's instructional. Like you said, it's like not everybody is going to know about this, but this is very important.
Yeah. Yeah. And, I sat with it for a couple of days and was like, well, do I use this for something? Because I was really worried. I was thinking, oh, TikTok, this is where kids dance, and this is where, it's not for scientists.
Yeah.
Um, but I decided to use it to answer some questions. I just sort of put out like, hey, everyone, by the way, I don't know anything about masks really. Like people were asking, like, do they really work? Do I have to wear one? And I was like, let's talk about neuroscience instead, because that's what I actually study. And I started answering questions, and it just sort of went from there. But to your point about the science always changing, I get so nervous because really when I'm talking about
You're
something,
documenting something.
yeah,
Yeah.
it's like, especially as a person who studied autism in my PhD, in 1998, a paper came out showing that the MMR vaccine causes autism. And so if I had a TikTok at that time, I might have come out and said, look at this new research. And it would have turned out that I was contributing to the problem, because it later, like 12 years later, it turned out that paper was falsified data, and there is no link between the MMR vaccine and autism. It's now been shown. But I worry about the same thing happening to me. It's like science is constantly changing. I mean, in that case, the science wasn't changing. It was a falsified study. But we don't know what we know today will be true in 10 years. And so I view it as extremely important to get science to the public, especially now because, there's paywalls and there's jargon. And if the average person who's not a scientist wants to learn about science, really the only way that they have to do that is by reading like media articles about it. And in fact, sometimes those media articles aren't actually accurate. I've seen inaccuracies a lot of the time. So I feel that it's really important and sort of on the shoulders of scientists to make this stuff accessible. But I do worry about, showing, because you never know what's going to go viral too. I might post a video that gets 6 million views. And then a year later, a study comes out contradicting it. And I'm like, okay, time to correct my original video. And I post it and it gets 20,000 views. And it's okay. Now there's 5.9 million people out there who I spread misinformation. Now, what is now misinformation too? So, I just try and do my best, but it is kind of frustrating when the platforms, these social media apps, are a little bit unpredictable.
Yes. And I think I just appreciate your humility. I think this is really very common in the science world, but also sometimes missing is this like this there is no absolute. Like we are learning along with everyone else and maybe hyper specializing in something, but even in that specialty, things change. And even research, by the way, is not, some is better than others. And,
Hmm.
people will quote research and it's kind of like, look at like the study. If it's studying 20 young males and saying this doesn't correlate with knee pain, but they're studying 20 young males, I'm not sure that's a really beneficial pool to look at.
Hmm.
And but I think it's so important for people to realize like you're offering a service for free to help them, and it within that there should be an understanding like there's always things that will be added, subtracted, or changed because that's the way science is. It's growing, it's changing, and we have to do it. But based on what we know now, this is what we know to be factually accurate. So I appreciate your humility in that, and
Oh,
nobody's going to
thank
hold
you.
you accountable. I promise. Well, thank
Thank
you
you.
so much for your time today. I know you have a full schedule, and just let everybody know this will also be in the show notes, but where they can find you on these social platforms and website anywhere else.
Yeah, um my social media handles are very similar but different across platforms. So the best thing to do is just go directly to my website, which is my name, Ben Rein, BenRein, .com, and you can access all my social media profiles and everything from there. You can actually also download my research papers if God bless you, you want to do that. Um, and there's also resources for students on there. If anyone here is a student in science, I have some resources on there. But yeah, thank you so much for having me. It's been fun.
It has been fun. I could talk about the brain all day. Thank you so much, Dr. Ben Ryan. And as always, for all of you listening, I'm pulling for you.